So we'll basically be looking at the concept of electric charges. And in general, you are all aware that you have different types of particles that you've covered in science before, being protons, neutrons, and electrons. If we're focusing on the electric charge, then what charge is a proton?
Positive.
What charge is on a neutron?
No charge. Charge.
And what's the charge on an electron?
Negative.
Right. Now, do you guys know how much the charge is on a proton and an electron?
1.
So Alicia says 1. Yvonne?
Yes, 1.
All right. So for the moment, I assume all you've been taught is that it's called +1 and -1. Now that is a relative charge. So, you know, it's a nice kind of number to work with. And so because, you know, you are both comfortable with the fact that you either get 1 electron or 2 electrons and so on. But this 1 actually, you know, what unit is it in, right? I mean, if you say it's +1 or -1, what's the unit? Any idea? So we will be talking about this, and this is partly what we'll be going into now. So we will now be discussing what a unit of charge is, and then actually expressing it in those units. But before you've learned that basically, you know, a proton is a positive charge, and each one is the same, and we just think of that as a 1. Think of it like an X, basically, right? You don't know what X is, but think of it like an X, which we'll call 1 for the moment. An electron has a negative charge, which is the same amount, but negative. And again, it's like an X. And basically, for the moment, until you do, you know, late year 12 stuff, that's basically your basic unit of charge. That you don't really know of any charges that are smaller than a proton or an electron at this point in time. So you're also all very comfortable with the concept of atoms. So atoms, what makes up an atom, Yvonne?
A nucleus.
So you've got a nucleus, which is big or small?
Pretty big.
In size?
Relative to an electron.
Yeah, okay, relative to the atom?
Yeah. Oh, small.
Yep, wow. So you've got a nucleus, which is quite small, as well as, and then what happens, Alicia?
Electron shells.
All right, so I just draw 1 as an example. Now, obviously, you may know that electrons don't really kind of orbit like this, but the point is you've got a region called the nucleus where you've got protons and neutrons, which is confined to a rather small space, usually in the order around 10 to the -15 meters. And then you've got electrons going outside, which we would then assume to basically be, you know, determining the size of your atom, which is also not that big. It's generally around 10 to the -10, which means that the nucleus is about 100,000 times smaller than your atom, which means if you're in an average sized room, like where you might be at the moment, you know, then 100,000, so if your room is like 5 meters, right? Or maybe more, then basically 100,000 times would make that 500 kilometers. So essentially, if your room is the nucleus of an atom, your atom would go all the way to Coffs Harbour. Kind of, that's the idea. And if you don't know where Coffs Harbour is, well, just think of it as almost getting outside of New South Wales. Pretty much. That's the rough idea. You have to go further than Canberra if your room is like 5 meters. All right, so that's your atom. And are atoms charged or not charged?
Not charged.
Yep, but of course they're made up of protons, which are charged, and electrons, which are also charged. And so the reason they aren't charged is because, I'm sure you both know, they cancel each other out. And so we say has no net charge. Okay, so give me a moment. So an atom has no net charge. And that's basically because it's got an equal number of protons and electrons. And neutrons we don't really care about in the case of, charges, because they're simply uncharged. It does make a difference for a mass. All right. And so in general, because protons are in the nucleus, so they're fairly immobile. And so usually under most circumstances that we're discussing here, it is usually the electrons that move. And so if you lose electrons, then you become positively charged. And if you gain electrons, then because you now have an imbalance between protons and electrons, you then become negatively charged. All right, so that's essentially the idea behind, charges. Now, we also need to cover things that I'm sure you do know, but let's be very clear here. If you have charged particles, and we will call these electrostatic charges, you have a possibility that they are positively charged, and you have a possibility that they are negatively charged, and anywhere in between, including not charged. But assuming they're charged, you've only got these two options, either positive to some amount, or negative to some amount, or, not charged. Now, how do they interact with each other?
They attract.
If it's positive and negative, they will attract. What other possibilities are there?
Repel.
When?
They're the same charge.
Right. So this is often abbreviated as opposite charges attract and like charges repel. All of this, I'm sure you guys know. Right. So now, we want to now talk about a unit of charge. And so basically, what you've talked about before, as far as this proton and electron thing here, I've basically said before that this is what's called a relative charge. It's also sometimes, it's basically the charge of a proton or electron, but you will also see it often called as a fundamental or elementary charge. And that's basically because unless you go smaller than an electron or a proton, which we can do now, then basically for a long period of time, for quite a long period of time, and certainly this has only been roughly the last 100 years, we basically considered that the charge of a proton or electron was essentially the fundamental charge, and you couldn't get smaller than that. That's no longer true, but it is basically a term we still use. And so we might use the sort of, you might see symbols like QP to represent the charge on a proton, P being the subscript, QE being the charge on an electron, and in general, Q in general represents charge. Have you guys seen this like letter Q before? Is that something you're familiar with? No. Okay. So Q is like, like S is for displacement, V is for velocity, A is for acceleration in your, kinematics chapter. In our chapter here, if you see the letter Q, it will represent charge. Now, the unit of charge is named after a scientist who did research in this area, obviously, and it's named after Coulomb. So the unit is Coulomb with a symbol of capital C. So that is the unit of charge. Have you heard of this before at all? Okay, yeah. So this is starting to get to the new parts of this sort of chapter compared to things you've learned before. Now note, a Coulomb is actually quite a large unit in size. So note, for most things, for many things, a Coulomb is quite large. And we won't get too much into the definition of what a Coulomb is, but we will say that your elementary charge is, and you can look this up in your reference sheet, 1.602 times 10 to the negative 19 Coulomb. So what we are saying is the charge of an electron or a proton is 1.602 times 10 to the negative 19 Coulomb. So, as a result, let me ask a different question. How many electrons are required to be, to be gained or lost so that a net charge of 1 Coulomb is gained? How would we work that out?
Is net charge the same as elementary charge?
No, by net charge, I basically mean that overall, just, how many electrons do I need to lose so I get 1 Coulomb? Now remember, an electron holds an elementary charge.
Is it that charge plus charge? How many electrons?
Yeah.
That charge plus the electrons divided by the charge equals to 1? No.
So let me rephrase the question, all right? So let's say that if every, every bottle has 50 mils, right? You've got small bottles. Every bottle is 50 mils of your, soft drink, right? Let's say. How many bottles do I need to get 1 liter?
Is it 1 divided by 1.602?
Right. It makes sense, right? This is the charge of 1 electron, right? So if you're not clear on what an elementary charge is, this is the charge on an electron or proton. One's positive, one's negative, but that's the charge on a proton or an electron. And so if I want to know how many I need to get 1 Coulomb, it's just, a basic math problem, right? In the same sense that if you need to know how many bottles of water you need to get 1 liter of water, you just divide by the, volume that each bottle provides. So if it's 1 liter divided by 50 mils, that would require 20 bottles. And in this case, the number of electrons I would need would just be 1 Coulomb divided by, the 1.602 times 10 to the 19 Coulomb per electron, if you like. And that will give you a big or small number.
Big number.
Right. And if you do that, you'll hopefully find that the answer is approximately 6.24 times 10 to the 18 electrons. So as we're saying, an electron carries a charge, which we will call in our sort of parlance, elementary or fundamental charge, although it's not quite as fundamental as it used to be because it can be broken down further. And a proton carries an equal amount of charge, but positive. Charge is represented by the letter Q, and Q, you know, can either be positive, negative, or zero. And it's measured in coulombs, which has a symbol of C. Because it's quite a large unit, the charge on an electron is quite small when measured in coulomb, and that means you need a lot of electrons, being 6.24 times 10 to the 18 electron, to move to get 1 coulomb. All right, everyone happy with that? Okay. Now, we need to talk about the difference between electrical conductors and insulators, although I imagine that this is something that you're both familiar with. So, what is an electrical conductor, Yvonne?
An object that allows the flow of electrons through it.
Well, typically yes, but not necessarily electrons. But basically it allows, we'll just keep it simple for the moment, allows electricity to flow through it. And usually it will be electrons. How is that different to an insulator, Alicia?
Electricity can't flow through an insulator.
So does not allow electricity to flow through it. So that's the answers you guys have given me. So can you give me an example of a conductor, Alicia?
Like metal wire.
All right. So typically, what are your metal wires made from?
Copper.
Copper will be the most common one in most situations at home. Can you give me an example of an insulator, Yvonne?
Like wood.
Any others?
Plastic.
Yeah, any others?
Glass.
Mm-hmm. Would you consider air an insulator or a conductor?
An insulator.
All right. You guys are all pretty happy with that, right?
Yeah.
So, I mean, that answer might be sort of okay, and it does have the general sort of idea. And I know why you guys have talked about electrons, because, you know, we will need to talk a little bit about how electricity conducts, and for the general things like metals in particular, we're saying, you know, it is basically electrons for the majority of time. I'm just not sticking to electrons purely because there are times when it's not electrons, but the need for the things you do study, the vast majority of the time it is the electrons that flow. Having said that, given these definitions that you've given me, we're saying that air does not allow electricity to pass through, yes? As an example, yeah?
Yeah.
All right, now, when it rains and you have a thunderstorm, what sort of thing happens?
Power outage.
Well, not necessarily. Hopefully not, but that could happen. Anything else that happens when there's a thunderstorm?
Lightning.
Yeah, you're going to get lightning, right? You're going to get rain, you're going to get lightning. What is lightning?
The transfer of like electricity, like the charge through the earth, like into a tree back into the earth or something.
Well, we don't know exactly without, but essentially lightning, you're saying relates to electricity, right?
Mhm.
And, it could be a tree, it could be, until I give you a specific example, it could be between, the tree, for example. And potentially this is a very non-scientific diagram, but you get the idea. So we're basically saying that maybe it's potentially electrons, going from, or electricity going from one place to the other, right? And we're saying that's what lightning is, isn't it?
Yeah.
Now, we're not being too scientific about this. Having said that, though, if you have lightning, what's it going through in our diagram and in your
The air.
it's going through the air, and in our diagram we said it goes through a tree because the light might strike a tree. So what's it going through there?
Wood.
Wood. But did you guys not say that wood and air are insulators?
Mhm.
So is that contradictory, or do you want to sort of clarify your answers? Because if you get it, then it's fine. But I just want to make sure that, some students, this really confuses them because they haven't really understood that. So I'm just trying to figure out what I would like to know is, would you like to clarify your answers? Or if your answers are to be left as is, then doesn't this contradict that?
Is it like it can insulate to a certain degree?
So that's what. No idea?
Oh no.
Right. So Alicia's on the right track. So basically, you need to understand that when we do very simple things like, say things like conductors or insulators and so on, these are qualitative terms, right? You probably understand that not all metals conduct as well as each other. There are metals that conduct better, such as copper is quite a good conductor, which is part of the reason why we use it for most of our wires. And some metals are even better, like silver, but they can be expensive. That's why we don't use them, not because it's very good. And something like iron, while decent, is not as good as copper. All right, that's why we don't use generally. We could at certain times, but a lot of the time we don't use steel wires if we have a choice. Electrical insulator, so wood, plastic, glass, air, they're all insulators, but again, they're not all as well insulating as each other. So you need to understand that with these things, almost all the time, most of the time, if not all the time, it's not black and white. There is gray. So in other words, we might very easily kind of split things up into what are called conductors, and we might call them into insulators. And in very simple terms, we will say that a conductor conducts electricity. And in very simple terms, we would say an insulator does not conduct electricity. But you should understand that as far as conductors go, some conductors are better than others. And as far as insulator goes, some insulators are better than others. And what if I've got, a conductor that doesn't quite conduct as well as where I might draw the line? What might go here in between?
Semiconductor.
So yes, semiconductors would be kind of what we call semi in the middle. And we don't do too much of that today and in this topic, but indeed, you have what are called semiconductors, like your silicon and your germanium, that would fall in the middle. Can you think of anything else other than semiconductors which might sort of fall in the middle?
Water.
Right. You're often told that, you don't want to touch, wires when you're wet because, water makes it more easy for electricity to flow through you. Having said that, you don't exactly use water as a wire, right? It doesn't conduct very well. So Alicia is basically on the right track. Essentially, we split them into groups of conductors and insulators, and we might say in very simple terms that this does and this does not, but more properly, this is conducts electricity sort of easily, if you like, and this does not conduct electricity easily. So that's kind of one way to sort of describe it. And then the other thing is so far, are we talking, is this a qualitative or quantitative measure?
Qualitative.
Right, it's qualitative. And as you can probably guess, in science, even if we start with qualitative ideas, we do want to have some sort of quantitative measure to describe, you know, how well they conduct, or for that matter, not conduct, insulate. And as with anything, if, you know, there is a limit, so we'll talk about how we might break down that limit, but essentially, insulators have their limits as well. And that is why air, under the extreme stresses of lightning, will then still allow you to pass through. Now, do you guys know how we might sort of describe this, how well something conducts and how poorly it conducts? Do you know any words that you may have come across before?
Volt, like a voltmeter.
So a voltmeter measures voltage, and so clearly it's a concept you've come across before, which we will revisit, but a voltage doesn't actually refer to how well something conducts or not.
Like the conductivity.
Yep, so conductivity is a word that you may have come across before. So this will, on this end, you'll have high conductivity. And this end, you'll have low conductivity. Having said that, conductivity basically is basically going to, when we look at the concepts later in the chapter, going to be a constant for each material, which basically represents how well the material conducts electricity, essentially. Now, having said that, if you have a piece of wire, what do we refer to for that wire? We don't normally, the conductivity normally refers to the material. If we have a piece of wire, we refer to the watt of the wire, usually. Starts with R.
Resistance.
Right. So if it's a conductor, does it resist a lot?
Yeah. No.
Yeah. So this is low electrical resistance. And on this end is high electrical resistance. Now, while we're on this topic, I assume when we will revisit this later, but I assume electrical resistance is the concept you guys have come across before. Do you guys know what unit it's measured in? Did you guys do this before and also, you know, do calculations with resistance and voltage and other things in previous years?
Sort of, I think. I forgot most of it.
I remember.
Yep. So part of that will be revisited later in this chapter, but just as a quick recap, electrical resistance is measured in ohms.
Oh, yeah.
Does that ring any bells?
Yeah.
Do you guys remember the symbol for it?
Like a U? No.
Not a U, it's a Greek letter. That looks like that.
Oh, like a...
So the things that you guys have forgotten from previous years, you know, an ohm, does ohm ring any bells? Apart from being a unit of resistance, does it ring any bells for anything else?
Is there a law associated with it?
Yes, there is. There is Ohm's law, which is, again, something I think you may have done in prior years. But all of those things are things that are to come later in this module. So don't worry if you've forgotten, we will be doing it again. But just if you guys have, you know, done this before, then hopefully it will be easier this time around. So just reiterating, an electrical conductor is something that allows electricity to flow through it, or which really means allows charge, I suppose, to flow through it. More properly, it means it allows it to flow through easily with low resistance. And an insulator will therefore provide a high resistance to, a flow of charge, or therefore for electricity to flow through it. And typical examples would be metals for conductors, and things like wood, plastic, glass, air as examples for insulators. As situations like lightning demonstrate, for example, even insulators, it doesn't actually, just because they provide a high resistance to flow, doesn't mean they can't flow. It just kind of means it's harder for it to do so. And so under sufficiently strong circumstances, then it will still flow. Kind of a bit like how when you have your sort of turning switches on and off, do you ever see a spark when you turn a switch on and off?
Yeah.
And so when you see a spark, that's electricity going through the air. And that causes a spark as well. And you guys may have seen either in videos or in previous science experiments with like a Van de Graaff generator, where you kind of put your finger close to it, and then when it gets charged up enough, it creates a spark. That again is electricity flowing through the air. So in case it confused you before, hopefully it's clear now. Electricity can theoretically pass through anything depending on the circumstances, but it will be harder to pass through certain things with high resistance, which we'll call insulators. It'll be easier to pass through certain things with low resistance, which we'll call conductors. Now, conductors, therefore, provide low resistance to a flow of charge. And one example of that is electrons can flow. And we will need to briefly talk about this, but I'm sure you guys know. For example, metals. Why are metals conductors? Yvonne had kind of given me an answer a bit before. So Alicia, can you tell me?
The delocalized electron.
Right, and this basically ties in with your chemistry. So I won't go into it too much, but you basically just need to refer to the fact that of its structure, of its basically the fact that it's got cations surrounded by, delocalized valence electrons. And because the delocalized valence electrons are free to move throughout the structure, therefore, in general, it's not bound and not fixed in place. Therefore, the electrons are charge carriers. And therefore, negative charges in the form of electrons can easily flow from one end to another. And that, is something that you may need to explain, but I don't think it's something you guys have much trouble with. Now, on the other hand, take an example like an insulator. Why is an insulator, on the other hand, why doesn't it allow electrons to flow easily? Why does it provide high resistance, Yvonne?
Is it the opposite? Is it because electrons can't decay?
It is, but why? You need to give me a bit more detail in terms of structure.
Utilized in bonds or on the atoms.
So you broke up a bit, but I think you're on the right track. Essentially, you don't need to go into too much detail unless they give you a specific one. But essentially, they are often, the electrons are held tightly within bonds. So e.g. in your covalent bonds, depending on what type of material you're talking about, and are therefore not mobile. And not free to act as charge carriers. And as a result, if you can't act as charge carriers, then charge can't get from A to B, and therefore it's an insulator. Does that make sense? Okay. Good. so that's your brief introduction. And then the next thing we'll be moving on to is Coulomb's law, which you may have done before, but looks like we need to revise.